Routing is the process of selecting the best path for data packets to travel from source to destination across an interconnected network. Routers are the key devices responsible for forwarding packets based on the destination IP address. IP addresses are essential numeric labels that identify devices connected to a network. The two primary versions of IP addresses are IPv4, consisting of 32 bits, and IPv6, with 128 bits. IPv4 addresses are currently more prevalent in use, and they are represented as 4 sets of decimal numbers separated by periods, such as 192.168.0.1. However, the rapid growth of the Internet and connected devices has led to the exhaustion of available IPv4 addresses. To address this, IPv6 was introduced, providing an incredibly vast pool of unique addresses. IPv6 addresses are represented in hexadecimal format, separated by colons, such as 2001, 0db8, 85a3, 0000, 0000, 8a2e, 0370, 7334. As the migration to IPv6 continues, it ensures the continued growth and scalability of the Internet by accommodating an exponentially larger number of devices, overcoming the limitations faced by IPv4. Routing tables play a vital role in the operation of routers, guiding them in determining the optimal path for forwarding data packets. Each entry in a routing table contains essential components necessary for efficient routing. The destination network field specifies the IP address or subnet to which the packet should be sent. The next hop field indicates the IP address of the next device or router responsible for forwarding the packet towards its destination. The metric cost value represents the desirability of the route, with lower values signifying better paths. Routers use this metric to select the most efficient route for packet delivery. The routing table serves as a decision-making tool, enabling routers to make informed choices about how to route packets through an interconnected network of devices. In the provided example, we see 2 entries in the routing table, showing that packets destined for the subnets 192.168.10.0/24 and 192.168.20.0/24 will be forwarded to the next hop devices with IP addresses 10.0.0.1 and 10.0.0.2, respectively, with corresponding metrics of 1 and 2 indicating their desirability. Static routing is a straightforward method of configuring the routing table on a router manually. It is well suited for small networks with relatively stable topologies and few changes in network connectivity. In static routing, network administrators explicitly define the paths that data packets should take to reach their destinations. The provided example demonstrates the configuration of static routes on a Cisco router. With the IP route command, specific destination networks are defined along with their corresponding subnet masks. The next hop IP addresses are also specified, indicating the specific router interface or gateway through which the router should forward packets destined for the defined networks. While static routing is easy to set up and understand, it can become cumbersome and less scalable in larger and more dynamic networks that experience frequent changes in topology. In such cases, dynamic routing protocols like OSPF or BGP are more appropriate as they can adapt to network changes automatically. Dynamic routing is a network routing technique that enables routers to automatically exchange routing information, allowing them to adapt to changes in network topology dynamically. One widely used dynamic routing protocol is the Routing Information Protocol, RIP. Enabling RIP on a Cisco router involves a few simple steps. First, the router RIP command is used to enter the RIP configuration mode. Next, the version 2 inches command is employed to specify the use of RIP version 2, which supports the use of classless IP addressing. Lastly, the network command is utilized to advertise the network is that the router is directly connected to and wants to participate in RIP routing. By exchanging routing information with neighboring routers, RIP enables routers to build and maintain an up-to-date view of the network topology, facilitating efficient packet forwarding and path selection. While RIP is easy to configure and deploy, it may not be as efficient as more modern dynamic routing protocols like OSPF or EIGRP, especially in larger and more complex networks. A default route, or gateway of last resort, serves as a fail-safe option for routers when they cannot find a specific route for a given destination in their routing table. It acts as a catch-all route, that directs traffic to a predefined gateway when no other matching route is available. The configuration of a default route involves the iproute command, where the destination network and subnet mask are set to all zeros, 0.0.0.0, to indicate any destination, and the next hop IP address is specified as the gateway through which the router should forward packets when there is no specific route. In the provided example, the command iproute 0.0.0.0.0.0.0.0.0.254 configures a default route with a next hop IP address of 10.0.0.254. This default route becomes a critical component in ensuring that packets find a way out of the network, even when their destination is not explicitly listed in the routing table. It is commonly used in scenarios where routers need to reach destinations beyond their immediate network and rely on a central gateway or router for further routing decisions. Further administrative distance, AD, is a critical concept in routing that helps routers determine the trustworthiness of routing information from various sources. It is a numeric value assigned to each routing protocol, representing the reliability or preference level of the information provided by that protocol. When a router receives multiple routes to the same destination from different protocols, it uses the AD to decide which route to select. Lower AD values are considered more reliable, and the router chooses the route with the lowest AD as the best path to the destination. For instance, directly connected routes have an AD of 0, making them the most trustworthy. Static routes have an AD of 1, indicating their preference over routes learned from dynamic routing protocols. In the context of some common dynamic routing protocols, RIP has an AD of 120, OSPF has an AD of 110, and EIGRP has an AD of 90. By utilizing administrative distances, routers can effectively prioritize routes and build a routing table that ensures optimal path selection and efficient packet forwarding. Routing loops are a serious issue in computer networks that can disrupt the flow of data and lead to packet loss. They occur when packets are stuck in an endless cycle of being forwarded between routers without ever reaching their intended destination. To prevent such loops, routers implement various mechanisms as part of their routing protocols. One common technique is split horizon, where a router does not advertise a route back to the same interface from which it was learned. This prevents loops from occurring on multi-access networks, where a router might receive its own updates. Another method is route poisoning, which involves advertising unreachable routes with an infinite metric, signaling to other routers that a route is no longer available. This quickly propagates the information about a failed route and helps to update routing tables accordingly. Additionally, routers use hold-down timers to prevent rapid and frequent updates in response to route changes. When a route is declared unreachable, the router enters a hold-down state during which it ignores any updates for that route, giving the network time to stabilize and preventing incorrect route information from spreading rapidly. By employing these mechanisms, routers can effectively mitigate routing loops and maintain stable and efficient data forwarding within the network. Route summarization, also known as supernetting, is the process of representing multiple contiguous subnets as a single larger network. This reduces the size of the routing table and improves network efficiency. To verify routing configurations on Cisco routers, several helpful commands are available. The show iproute command displays the router's routing table, showing the various routes it has learned and the associated metrics. This helps network administrators understand how packets will be forwarded based on the current routing configuration. The show IP protocols command provides information about the enabled routing protocols, including OSPF, RIP or EIGRP, and their respective parameters and status. This allows administrators to confirm that the desired routing protocols are active and functioning correctly. Additionally, the show IP interface brief command offers a concise summary of all router interfaces, their IP addresses and status, providing a quick overview of the router's connectivity. To configure a Cisco router, access to its command line interface, CLI, is necessary. There are two main methods to achieve this. First, console access involves connecting a console cable from the PC's serial port to the router's console port. Terminal emulator software like PuTTY or SecureCurt can be used to access the router's CLI through this console connection. Alternatively, remote access is possible if the router has an IP address and is reachable over the network. Remote access can be established using either SSH, Secure Shell, or Telnet protocols, allowing network administrators to configure the router from a remote location. These access methods are essential for efficiently managing and configuring Cisco routers in various network environments. Configuring a router involves several essential steps to ensure proper functionality and security. First, entering global configuration mode is necessary to start the configuration process, achieved by entering the enable command to elevate privileges, followed by configure terminal to access global configuration mode. In this mode, users can configure various aspects of the router. Next, setting a hostname and a banner message is essential for identification and informational purposes. The hostname is configured using the hostname command, and a banner message is displayed to users when they connect to the router, enhancing security by providing warnings or notification. Securing the privileged exec mode is crucial to prevent unauthorized access to critical router functions. This is achieved by setting an enable password using the enable secret command, providing an additional layer of protection. Ensuring security on console and VTY lines is also vital. The line console 0 inches command allows setting a password for the console interface, protecting access to the router's physical console. Similarly, the line VTY 0 4 inches command configures password protection for virtual terminal connections, VTY lines. Finally, configuring interfaces is essential to enable communication with other devices. The interface command followed by the interface identifier, such as Gigabit Ethernet 0/0, allows configuring an IP address on that interface. The IP address command assigns the desired IP address and subnet mask to the interface, and no shutdown activates the interface. This step is necessary to allow the router to communicate with other devices on the network. After making configuration changes on a router, it is crucial to save those changes to the router's non-volatile memory so that they persist even after the router is rebooted. This step ensures that the desired configuration remains intact and the router operates with the intended settings. The command to save the running configuration to the startup configuration is copy running config startup config, commonly abbreviated as copy run start or write memory, or simply WAR. This action copies the currently active running configuration, the configuration currently in use, to the startup configuration, the configuration that will be loaded upon the next reboot. By doing so, any changes made during the current session are saved, and the router will boot up with the same configuration in subsequent sessions. Failing to save the configuration may result in the loss of changes made during the current session, potentially causing unexpected behavior and requiring reconfiguration after each reboot. Hence, saving the configuration is a crucial final step in the router configuration process to ensure that the desired settings persist and the router operates as intended. Imagine the routing table as a roadmap for routers. It is a data structure stored in a router's memory that contains information about various networks and the paths to reach them. When a router receives a data packet, it consults its routing table to determine the best path, next hop, to forward the packet toward its destination. A routing table is a crucial component in networking, used by routers to determine the best path for forwarding data packets. It contains several key components that aid in this process. Firstly, the network destination specifies the IP address or network address of the destination network to which the router needs to send the packet. Secondly, the subnet mask helps determine the size of the destination network. Thirdly, the next hop entry includes the IP address of the next router on the path that should be used to reach the destination network. The outgoing interface specifies the specific network interface through which the packet should be forwarded to reach the next hop. Additionally, the administrative distance is a numerical value representing the trustworthiness of the route source, with lower values indicating a more preferred route. Lastly, the metric is a measure of the path's cost or desirability, where lower metrics represent better routes. Together, these components enable routers to efficiently direct packets to their intended destinations across complex networks. To access and view the routing table on a Cisco router, you can use the command show IP route in the router's command line interface. When you enter this command, the router will display the complete routing table, providing essential information about how data packets should be forwarded. The output will include details such as the network destinations, which are the IP addresses or network addresses of the destination networks. It will also show the corresponding next hops, representing the IP addresses of the next routers on the path to reach those destination networks. Additionally, the output will list the specific interfaces through which the packets should be sent to reach the next hops. Alongside this information, the routing table will display metrics, which are measures of the path's cost or desirability. This allows network administrators to assess the efficiency and reliability of the routes configured on the router, assisting in troubleshooting and optimizing data transmission across the network. The first type of entry in a routing table is for networks that are directly connected to the router's interfaces. When a router interfaces with a network, it learns about the network's presence and automatically adds an entry for it in its routing table. These entries have a subnet mask of 255.255.255.0, or a prefix length like /24, because they represent specific interfaces' direct connections. For example, if the router is connected to a local network with IP addresses in the range of 192.168.1.0.24 through its Gigabit Ethernet 0/0 interface, the routing table entry would look like this. These entries are considered more specific and take precedence over other types of routes when forwarding packets to local networks. The second type of entry in a routing table is for networks that are not directly connected but are reachable through other routers, known as next hops. These entries provide information on how to reach networks beyond the local network. When a router receives a packet destined for a remote network, it consults its routing table to find the best path to forward the packet to the next hop router. The next hop router will, in turn, determine the best path to reach the final destination. An example of a remote network route entry would be here. The router has learned that the network October 10th 10.024 can be reached via the next hop 192.168.1.254 with a certain cost metric of 1/0. This metric represents the preference for using this route, with lower values being more preferred. The third type of entry in a routing table is the default route, represented as 0.0.000. The default route is used when a router doesn't have a specific entry for a destination network in its routing table. In other words, if a packet doesn't match any of the more specific routes in the table, it will be sent to the default route. The default route acts as a last resort option, ensuring that packets can still be forwarded, even if their destination is unknown to the router. An example of a default route entry would be, this means that any packet not matching any other routes in the table will be forwarded to the next hop router with the IP address 192.168.1.254, which is responsible for handling packets with unknown destinations. Routers dynamically learn and update their routing tables through routing protocols like OSPF, EGRP, or RIP. These protocols share information about networks, and routers use this data to build their routing tables. When a router has multiple available routes to reach the same destination in its routing table, it needs to determine the best path for forwarding data packets. This decision is made based on two key factors: administrative distance and metric. Administrative distance comes into play when there are multiple routing sources providing paths to the same destination. The router will prefer the route with the lowest administrative distance, as it indicates the reliability or trustworthiness of the source. For example, routes learned from internal protocols are generally more reliable than routes received from external sources. On the other hand, if there are multiple routes to the destination learned from the same routing source, the router compares their metrics. Metrics are values assigned to each route by the routing protocol, reflecting various factors such as bandwidth, delay, or hop count. The route with the lowest metric is selected as the best path since it represents the most efficient way to reach the destination. By considering both administrative distance and metric, routers can intelligently choose the optimal path to ensure efficient and reliable data packet delivery across networks. Clearing the routing table is a procedure used to remove all existing entries from the routing table of a router. The routing table contains information about various networks and the best paths to reach them. Sometimes it may be necessary to clear the routing table to start with a clean slate, especially when there have been significant changes in the network or when there are issues with routing. The command to clear the routing table is clear IP route *. This command is entered in the router's command line interface (CLI) prompt. When executed, it instructs the router to remove all the entries in its routing table related to IP routes. The asterisk is a wildcard character that specifies all entries, meaning it will clear the entire routing table. After executing the command, the router will have an empty routing table, and it will need to start relearning and updating the routing table using dynamic routing protocols or manual configuration. Clearing the routing table should be done with caution, as it temporarily disrupts the router's ability to forward packets until the routing table is rebuilt. It's typically used in specific troubleshooting scenarios, or when there is a need to reset the routing table due to some configuration changes. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.